Welcome to this lecture on digital system design in the course digital system design with PLDs and FPGAs. In the last lecture we have looked at what are the features of milli and Moore output, when can we use the milli output, and then we looked at the state machine controlling the data path through clock gating and recirculating mux, its advantages, disadvantages, how is the power dissipation and a solution for it, and associated VHDL coding and so on. Today we will address some more issues of the state machine. When you design, some things are related to kind of optimization, which sometimes the tool doesn't support, or tool doesn't support to a degree where it can be kind of used. You have to check whether your tool supports, otherwise you can try to implement this manually, which may be a little difficult in some cases, but at least to be aware of these issues will be useful when you are kind of in a difficult situation. So let us run through the slides of the last lecture before we get on to today's portion. So let us move on to the slide, and we have said that we have taken the example of our ADC controller. Here the Moore output, when the start comes, the machine transit to a particular state S1, and this start of conversion was made 1 and then it is made 0. So it is of 1 clock duration during S1, and since this is a function of the start signal, what we try to do was that we try to convert that into a milli type of output, and by making the SOC as a function of start, then we say that in this particular state S0 SOC is 1 if start is 1, and when the start is 1, upon the next clock edge it is transited to the next state S2, because S1 is not required, just to kind of make it equal and to compare. That is why I called this S2, because calling this S1 will kind of make it similar to that. And we have looked at the timing, and we have found that for the Moore kind of output, the SOC comes during the state S1, but for milli it comes during S0, and also we find that one state is less. So we said in general you have many outputs which are kind of milli outputs, then maybe the number of states in the state diagram will be less, so the state machine area will be less, and also the output comes earlier to the Moore in the case of milli. One other thing we have found, the problem was that if this particular input is not synchronous, then it can change any time, and if it changes very close to the clock edge you get a glitch at the output, and that can create problem. And that happens only when the input is not synchronous, and when the input is synchronous we could happily use these. Suppose in this case we are showing the FSM 2 synchronous subsystem. As I said, it could be registers, counters and all working in the same clock, then some output is coming, and we can now generate this particular output of the FSM as a function of these synchronous inputs. So wherever you have synchronous input you can generate the output as milli type output, which will have better timing. It comes earlier, and it has number of states less and so on. And we have also seen how the state machine generates some enable signal. In particular we have looked at the register, how this latch signal enables the latching the data from the input side. So that is what we have shown. We have a register and an FSM working at the same clock, and this latch signal is decoded from a state which is controlling the register. So when the latch is high and the clock comes, the data gets latched, and a possible implementation was this, and we have found the problem with it, that it has two kind of active edges come here. The first one may not meet the kind of the timing requirement for the data. Second one could create timing problem, and if this is used, I said, to clock a counter, it might kind of count twice and so on. And the solution is a recirculating mux where we moved the latch signal or enable signal in the data path, and that works properly because that is enabling the input to the input of the register, and neatly in the next clock edge it is latched, enough time is there. The only issue with this was that it is clocking all the time, either it is connecting the input to the register or it is recirculating, and this idea can be applied to kind of any number of inputs, not only just enable. So we are showing this as an enable of a counter. When the enable is 1 which has to be synchronous with the clock, and then the counter is incremented, and that's very useful kind of situation that we are keeping track of, the state machine is keeping track of some event and event has happened, and then we enable the event counter so that the counter can be incremented. Because say we are working on some communication issue and we are counting the number of bits, so when we have kind of done all the processing, then we can increment the bit counter and so on. There are a lot of applications can be used, and we have seen the corresponding code, and we have also looked at, we have limited to enable, we have another load signal, then another mux come which has priority, so it comes close to the D input of the flip flops. So then we have seen the equivalent code, and we said that the problem with this recirculating mux is that a lot of power dissipation, and this actually is much better in the power dissipation, because only when it is enabled it switches, it dissipates power. The issue is that it has kind of two edges. So if you move this to the negative edge side, then if you AND it, then you get a single pulse, okay, the correct location. So we decided to resynchronize this enable signal with the negative edge of the clock, then this will move here like that, and if you AND it you get a neat pulse, and that's what we have done in the next scheme here. So the clock, this is a negative edge triggered flip flop, and the enable signal is given to that, so it is resynchronized to negative edge clock 1, that is ANDed with the clock, and that is used for clocking the register. So that is what is shown here. This was the original enable signal and it is given to the input of this D flip flop. So since it is negative edge triggered, at this edge this is latched, so there is a TCQ delay, it appears here, and this edge it is kind of this edge that is the 0 is transferred here, so you get it here, you AND with the clock, this clock 1, that is what we do, and the clock 2 is a neat pass and a single pass you get. So this is a kind of clocking scheme for low power, and as I said, whether you write a VHDL code for this or VHDL code for this, many a times can convert this into kind of this particular circuit. At the VHDL code level itself it can be converted. It's very easy to do that, and the tools can do it automatically. So that is where we have kind of stopped in the last lecture, and let us move on with some more issues of the state machine. And once again, before going to that, just a reminder, the state machine structure is like this. You have state flip flops, keep track of the state, the output is a present state which is combined with the input and generate the next state which is latched on the next clock. So this is kind of one path, and the next path is that the present state along with the input is decoded for output, and if it is Moore output it is only present state which is decoded. For the Millet output, both input and the present state is decoded, and we said if you look at this logic and this logic, both receive the present state and input, and so we can combine this logic in one block. Only thing is that this output is shown from there. So that is what is shown here. This logic comprises of next state logic and output logic. The next state logic will give next state, the output logic will give the output. Both are useful for analyzing, writing VHDL code and so on. So please keep both in your mind. Some textbook show this and some textbook in your basic courses show this. Doesn't matter, but then it is better to keep both views in your mind. So let us take up this issue, the state diagram optimization. So when you kind of come out with a control algorithm, like we have seen that you have a problem specification, then we said that you draw a waveform of the input and output, and looking at the waveform you can write a verbal description of what we are intended to do many a times, and that's algorithm. Formally put it, that verbal description can be turned into a proper algorithm with iteration and all that, and you draw it, and many a times it can be complex, and at least at the first stage when you do that, when the control algorithm is little elaborate, complex, and you draw the state diagram, it may happen that there are identical states in different parts. Different parts means assume that you are in a particular state, depending on the input you branch to different kind of sections and do something, okay. So it may happen that in one state, in one section is similar to another state in another section, and because it is many a times you draw it on a paper, it is very difficult to kind of identify that both are kind of identical, okay. So the tool can do it. Tool can detect the kind of identical, or we can even call equivalent. Identical is not a good word technically, but we can say equivalent states, okay. Now the question arises, what are the equivalent states, okay. Definitely from your kind of experience with the state diagram, we can say two states Si and Sj are equivalent. At least we can say if they produces the same output, okay. If it's more, then it just produces same output, or we say if it's a milli kind of output, then we say two state for the same input condition produces the same output. We cannot say they are equivalent, at least they are half the job is done. With regard to output, now we have to look at the transitions also, okay. Now if you look at the transition, there are two cases. There could be two states which are transiting from the same previous state, and there could be two states from which the transition occurs to the same next state, okay. So for an equivalent state, which one to consider is the question, but it is very easy. We know that the next state is a function of the present state, okay. So if two states has to be equivalent, they should produce the same next state, because next state is a function of the present state, okay. So if two present state produces the same next state, then in that next state Boolean equation this present state appears. So if they are identical, I mean the next state is identical, then we can say these states are equivalent. So let us put whatever I have told formally. So let us go to the slide. So we say states Si and Sj are equivalent if for the same input condition both state transit to the same next states, okay. Now when I say same next state, Si and Sj can transit to Sk under the same input condition. That means like we discussed earlier, there may be an input signal called start, and Si and Sj will remain in their states when the start is low. When the start is high, Si transits to Sk, Sj transits to Sk. Say assume that these are different parts of the state diagram, okay. Not that, don't assume that both are kind of concurrently working. When the state machine in Si and the start comes, it goes to Sk. When the state machine is in Sj and the start comes, it goes to Sk. Okay, now that is just the simple case. Maybe Si transit to not only Sj, on some other input condition it might transit to, sorry, Si transits to Sk on some condition, Sl in some other condition. So Sj also should transit upon the same condition to Sk and Sl. So all the transition, all the input condition should match, okay. That is the then we have to state the output for the same input condition. Both states produces the same output, okay. For more output you can ignore the input condition, does not matter. With the more output we do not decode the input, so only the present state matters. So that is, then we can say Si and Sj are equivalent. That means for both states transit to same next state for the same condition, okay. All the transition, all the conditions should match. These two should produce the same output for exactly same, for the same input condition. If it is Mealy, if it is Moore, just same output. Then Si and Sj are equivalent, then we can replace Sj with Si. You know, that's a game, you know, that's simply wherever Sj is there, rub it off and you know, bring those arrows, whichever was going from Sj, anyway it goes from Si, and the output also is taken care, there is no problem, it works properly, okay. So that is how, so if Si and Sj are equivalent, one is redundant, you can remove it, and the rule is applicable to more than 2 states. When we formally state, we say about 2 states, but then it's easy to kind of formally state it, but if 3 states can be identical under the same kind of condition. Now how to detect this? Now the question is that, fine, we say like in a state diagram, like you know that if there are 32 states spread across an A3 sheet, okay, you have drawn in a big sheet, and how do you look, you put the finger on one state and keep the other finger on all the other state and looking for, and you have to do all the combinations. It's a very laborious job. So on a state diagram it is very difficult to do that. Even if you kind of that does not help a computer algorithm, because ultimately if you want to do that in a tool, we have to formally state the algorithm. So which is the best place to look? So we know that the first one talks about the next state. So the ideal place to look for that is in the next state table, okay. So what are we looking? What we are looking for 2 states, at least let us take 2 states. The 2 state for the same input condition produces the same output condition. So you go to next state table, pick up the rows, okay, and wherever you find there are same next state and same input condition, and you pick up the present state. They are kind of the ideal candidates as far as the next state is concerned. So that is what I state here. The first condition can be detected by examining the rows, identical rows except the present state, because the next state is same and the input conditions are same. So you pick up all that, then you get the candidate for the present state, because we have to now detect whether the output is same, and that can be easily detected in the output logic output table. So the second condition can be detected by examining the rows, identical rows except the present state. So you leave the present state, look at the outputs. If outputs are same and the input conditions are same, then you can kind of for more output you can just look for the identical output, then you can pick up those states. Okay, now we have to kind of make an intersection of two states, because this at the end of it you get some states, if you look at it you get some state and both should be ANDed or intersected, then you get the correct thing. So this can be systematically done in an algorithm. So let us state that. So in the next state table look for the same next state, you look where all the next states are similar. Then out of this next state select the state which have the input condition same. So if you state an algorithm, look for the next state which are all similar, pick up all that, look at the input condition, wherever out of this input conditions are same, then you pick up the present state. Then go to the output table, check if the outputs are same for this next state. So wherever the outputs are same pick up those states, and then we have for Mealy you have to look for the inputs also, you have to match the input. For Moore you match the output, then these states where the outputs are same they are equivalent. So systematically you can do that. So the tools can do that. First look for the identical next state, then go for look at in these states the inputs condition in the next state table, if they are identical pick up those, go to the output kind of output table, check for these states where the outputs and input conditions are same, those states will be the equivalent ones, and you can remove keep one and remove all the rest, then the state diagram is optimized. You have to check whether your tool does it. Maybe when we come to the tool we cannot, I am waiting for some more portions to be covered so that we can introduce the tool, so that once for all we can try quite a few things. Also that that the tools are changing all the time. So I am in that part of the lecture may be less useful, because after few years if at all this course is used by someone, then the tool part is kind of, there is no guarantee that it makes sense, because by then the whole interface and everything would have changed. So people will have, still is useful to see the design methodology, the steps and the output and same. I am hoping that will be useful, but I am delaying it so that we pick up maximum information input so that you understand everything when I demonstrate the tools, boards and things like that. Okay. So let us move on to another issue. This we talked about the state diagram optimization. We have in a state diagram how to identify two or more states are identical, so that we can optimize the state diagram. We can kind of remove the redundant state and keep a minimal state diagram, so that the area occupied by the finite state machine is less. That is our aim. So let us move on to another issue which is called output racing or output glitches or whatever. So forget about the name, so let us look at the issue. Okay. So take a state machine with 3 flip flops. Okay. So let us call it, there must be Q2, Q1 and Q0. So I am just showing a part of a state diagram. So there, assume there is a big state diagram which kind of at least it has more than 4 states. We do not know whether it occupies 8 states, but more than 4 states, which force us to use 3 flip flop to implement it, and there are, we call it Q2, Q1 and Q0. Okay. Assume there is a transition from 001 to 010. Okay. So in this, when the clock, and there is no input condition, maybe a clock comes, this transit to this. So Q1 is going, Q0 is going from 1 to 0 and Q1 is going from 0 to 1. Okay. Now assume that, see, we have 3 flip flops and all may not be kind of has the same propagation delay, assume that the Q1 is faster than Q0. That means TCQ0 is less than TCQ1. Okay, the propagation delay of the first flip flop is less. Okay, sorry, the first flip flop TCQ1 is less than TCQ0 or TCQ0 is greater than TCQ1. So what happens is that you see that it was 001. If this is faster, this 0 will become 1 before this 1 becomes 0. Then ultimately 1 will move to 0 because the Q0 will change state after a while. So what happens is that in between while changing the state from 001 to 010, for brief period a transitory state will come which is 011. Okay. So that is what is shown in the picture. I have shown in the picture. I am saying that the propagation delay of Q0 is slower, I mean it is larger than TCQ1 or the Q1 is faster. So Q1 becomes 1 and for some time Q0 remain 1, then transit to 0. So 001 becomes 011 and ultimately it becomes 010. Very brief period it becomes, you know, and it happens, you know, that it is because you know, don't worry about it. We talked about in combination circuit, when there are multiple output there is difference in the path delay, it happens. So similarly when there are multiple flip flops because of the variation in the propagation delay of the TC flip flop, this happens. It is very natural. Okay, there is nothing wrong with this. Now you can take the other condition, if Q0 is faster than Q1. So take the other condition, Q0 is faster than Q1 means this 1 will become 0 before this 0 becomes 1. So you will get a situation where for a brief period you have all 000, then it transits to 001. So you have the other condition, the Q0 is faster, so 1 becomes 0, then the Q1 change state 010. So either of this condition, if the delay does not match exactly, one is greater than the other, there are two conditions, there could be a transitory state 000 or 011, and the fact is that we do not know whether these are kind of valid state. Maybe this is part of the state diagram, some other state. So you might ask, the question to ask is that is there any concern to worry about? Okay, it does not matter for a brief period, let this happen. It's only for a very few, maybe say 2% of the time or 1% of the time, it just, you know, transit, it does not, like it settles anyway. Okay, it looks little innocuous, but assume that these states produce some output. Okay, because this could be valid state in the state diagram or a part of our control algorithm. Assume that there are two outputs called enable and write, and that is one in this state which is valid. So what happens is that when the clock comes and the present state changes from 001 to 010, these outputs will briefly go active. Okay, so you see such a situation, here the state machine in this state, the clock comes, so for a, and ultimately this, the state here is 0, before was 001 and here it is 010, but brief in between it may go through 000 or 011. So if it goes through 00, you get a write pause briefly going high, a glitch, and an enable pause which is briefly going high if it happens this way. Okay. Now once again, is that a cause for a concern? You know, is that create some problem? Now it depends how this particular output is used. If this is used like to enable a counter, we know that it does not matter, because we know that when you enable something using clock gating or recirculating mux, nothing is going to happen, because we see, unless the enable stretches all over here, then only this clock will kind of become active, enable the recirculating mux. So it may not, in a synchronous case it may not kind of create problem, but we don't know how this is used. Maybe this is used asynchronously to increment a counter, or this write is going to an asynchronous memory as a write pulse. Then what happens that for a brief duration the write pulse go high, and if the access time is enough, maybe the address line is floating, or some value is there, data line is floating, but then something get latched into some address, and which can corrupt some location. Okay, so depending on how fast is the memory, how fast, how short is the access time, and so on. So this could create problem. So that you should keep in mind, because this is called output racing, because these two outputs, Q1 and Q0 is racing each other, and one is faster than the other. That can produce briefly the transitory state, it can produce output. This may or may not cause problem, and when there are critical applications we have to worry about it. Like you are making a kind of medical equipment which is used for some kind of radiation, and you are designing a controller for it, you have to be very careful. But if you are doing something very not that kind of where such a critical application is not there, it may not matter. It's some user intervention, user is pressing a key, if it's not detected maybe the user can press it again, may not matter. So it depends on the application, the criticality of the application, you have to break your head about it. Okay, always when you are designing something, maybe you are in a huge team. Okay, you are doing a part of the design, maybe you are doing front end design, you are doing the back end design, and you don't know, like some people sometime you do the back end design of kind of verification, and if you ask what is this used for, they may not be even aware which chip they are working on, or they vaguely know and they may not even know which is the application. It's very kind of very bad situation. If you are working on a design on a big team, you should know what are you working and what application it is used, so that you can kind of judiciously choose the design practices which is how the reliability, cost, flexibility, all that can be balanced properly depending on the application. Very very important. Like you are sending something to the space, and a space vehicle is being controlled, it's very critical, nothing can be corrected on the way sometime from the ground, so you have to make it very critical. So it depends where you are, or on an aircraft you have to be very careful. So let us go ahead. So this is what I have stated earlier. Now the question is that what is a solution? Now there is fine, there is an output race, what is the solution? Okay. Now when you have a problem, okay, when you have such a problem, and when you in general, okay, maybe you are used to always learning from the textbook, there is some problem, the textbook tell you some answers, but mind you these textbooks get the answer from the research somebody has done. At the beginning when somebody has proposed a state machine, Moore or Millet, all these issues would not have been thought about, that implementation kind of detail. But when you have a problem, you should know to solve it in the first place, you should know what caused the problem. Okay, then you can attack, find a solution. Say I have heard of a story, there was a highway and there was a sharp turn in the highway. Okay, the highway is very high speed highway is there, where the vehicles are going at very high speed, above say 100 km/h, and there is a sharp 90-degree turn for whatever reason, there is a turn, and at night there used to be a lot of accidents, and the residents are kind of worked out, they have to call the ambulance service, the police and so on. So the residents decided to do something about it, and they have met together, and somebody suggested that let us station an ambulance at the turning, so that when the accidents happen people can be picked up, and everybody liked the idea. It's a great thing, because whenever the problem happens they used to call an ambulance. So if an ambulance is ready nearby, this can be attended to. Okay. So everyone agreed, and they were going for kind of one collection to buy the ambulance, and some wise men said, see, the problem has occurred because there is a sharp turn in the highway. To solve, you have to straighten the turn, reduce the sharp turn, make it smooth, then there will be less problem, and everyone agreed, went about doing that. So similarly, when you have a problem, always think what caused the problem. There could be at least some solution to it, and let us see here in the output race what caused the problem. What caused the problem is that we can say that there is a, like it looks like that there is a discrepancy among the delay in the flip flop. There is a kind of variation in the propagation delay. Okay. Now if you once again, and this is not in our control, I mean you fabricate it and everybody try to fabricate it on the same die very close together, but yet when you do the processing, the like electrochemical processing, there could be a kind of variation. But if you think again deeply, you see the problem has come because there are two flip flops changing the state. That is why the variation in delay is affecting. Suppose the state assignment was 001 to 011, so 1 is not changing, only the Q1 was changing the state. So it shows that if the state transition can be logically adjacent, okay, or you say sometime the gray coding, if the adjacent states, like when a state transit from one state to another, if those states are logically adjacent, they change only by 1 bit, then this problem wouldn't arise. So at least like from working out from the fundamental cause, we can say the solution is that do state assignment such that more than one flip flop doesn't change output. Okay. Well and it is good, it works at least in simple cases. You have a state, a transit to next state, then a transit to next state, and so on, it comes back. Then you can do say 000, 001, 011, the gray code, and you can do that. Okay. But what about all kinds of transition? You have a state, then it transit to 3 state, from there it goes in a loop, from here it comes back to something. It may not be able to do the logically adjacent coding in all cases. And you take a simple case, you have one state here, it transit to next state, it transit to another state and come back. So 3 states are adjacent to each other. You cannot do a gray coding, because if you remember the Karnoff map where we do the logical adjacency for Karnoff map, we know that the 3 states cannot be logically adjacent to each other, 4 states can be. Okay. Maybe you will say you insert one dummy state in between which does nothing. It can be done, but then in a complex state diagram and you find there are a lot of kind of adjacency problem, you introduce dummy state and it becomes equivalent, I mean complex, and a lot of area is wasted on that, and that's not very bright solution. So if this is possible, if gray code is possible to do that, okay, it may not be possible, and then what we do is that maybe we can say another issue in the original diagram is that it is because it is producing output. Maybe there are some transitory state which doesn't produce or doesn't change the output, then do that the state assignment such a way. But very if a state doesn't produce any different output, what is the use of such a state? So though it looks sound very nicely, some solutions sound very nicely, but it may not make much sense. Many times when people talk, what they talk sound very good, but it may not be practically has no relevance. So you have to be very careful when you make statements. So this statement sound good, but practically it doesn't happen. If there is a transitory state which produces the output, same as before or same as after, then you may ask what is it doing, okay. It may not do any useful purposes. Suppose now assume that you can't do anything. What is the solution? Now you are stuck with this problem, you have a glitch, okay, then and that creates some problem and you want to solve it. What is the solution? So now then let us look at the ideal. Again what we look at is that how does a good output looks like. If enable is a valid output, it would have started from here, it would have gone all the way up to here. This is a transitory output, so it appears as a glitch, okay. If it is a valid output, it extends all the way at least for one clock period. So why not we put at the output logic one flip flop and give a clock to it, so that this if valid output is registered and get a registered output, this glitch won't be registered because it appears briefly for a short duration. So that's the kind of the most permanent solution. You output register the output, you know, and outputs are registered on the next clock edge well after the state change, but the output will appear after one clock period, okay. So that is what I have shown here. What we do is that you have the output logic, you put suppose there are 3 output, put 3 flip flops for 3 output, give the same clock and the reset, and this is the registered output. Earlier we used to take the output here, now you look at it. Suppose we have an enable output which is glitching, okay, and which is coming here. There is a load output which is a valid output, then you see the difference. Like since when the clock comes in this clock edge nothing happens, enable is not high. The next clock edge when the clock comes here, that this glitch would have disappeared, so the enable registered remains 0 throughout all the time. But if it is a valid output which starts at this point, goes all the way to the next clock period, at least this is the worst case, one clock period, it can remain high, does not matter. So in the critical case it remains there for one clock period, but when this clock edge comes it is high, so the registered version of that output comes at the output with a 1 clock cycle delay. So that means that all the glitches go off, but all the outputs kind of lag by 1 clock cycle, lag with respect to the state change, okay. But it's a less of a problem. You know that in the state diagram we come to the starting state, when it starts iterating or start initializing, everything is delayed by 1 clock period. As far as this particular output is concerned, not a problem, not a very serious problem, but you should keep that in mind. There can be side effect if you don't remember that, that little care has to be taken with respect to the timing. You have to analyze the timing, what happens, because you see that this output is going to the data path and data path is giving some input, and this latency can reflect some time in the control algorithm. So you have to take care, you have to think, don't take things just because you state solution is there, you put the output register and assume that everything works. You please analyze the timing. There you can think of situation where this makes a difference to the control algorithm, something need to be tweaked for proper work. You have to keep that in mind. If you are clever you can find a solution, maybe you can solve a very critical problem if you understand the issue. But now look at it, that's a permanent solution for output racing or output glitch. But one thing I want to kind of bring out from this diagram, earlier we said that this output logic and the next state logic gets an input, the same input, the present state is here and input here. The real inputs from the data path is input to this stage, input to this stage, and we combine this state here. So now if you look at this diagram, see this stage and this 2 stage look identical. So if you can take this output logic, put it here and call logic. Now that this flip flops and this flip flops are same, you get the clock and asynchronous reset same. So we can combine this here, only thing is that combines the output registering as well as the state flip flops. So that is what is shown here. Now with the output registering, the diagram looks much more simplified. You have a set of flip flops which combines a state variable. That means if there are 5 state, there are 3 flip flops, there are 3 for the state variables Q2, Q1, Q0. There are 3 outputs, then there are 3 flip flops for output, and this is the logic, which one part is the next state logic which decode the present state and the input and decide the next state which goes to the state flip flops, and there is output logic which look at the present state and input, produce the output which goes to 3 flip flops to register the output, and that comes here. Out of the flip flops come the present state and the registered output. But one thing you should remember, that one good thing happens here. We said that a set of registers with respect to the with a preceding logic can be coded in a single process. So though it looks very kind of complex with 4 blocks, when it comes to VHDL coding we can write a single process to implement this state machine. Okay, whether the tool detects it we have to check it, but at least from what we have learned it's a very nice thing. You can write a single process, and we will see that maybe in the next. I realize that maybe it is wise to discuss the VHDL coding of the state machine soon before we go ahead. Maybe in the next lecture we look at it, what are the possible ways of doing the VHDL coding, and this is very easy, like you write a process to code this register along with the next state logic and output logic. So it's a very simplified coding, and you want to generate a state machine with the registered output. The VHDL coding is very easy. Just put the state diagram and start writing the code, you will get it. So that's what we have discussed. Now the output registering, wherein when there are multiple flip flops change state in the same transition, then due to mismatch of variation in the propagation delay of the flip flops, there could be transitory state which can produce output glitches, and depending on how these outputs are used, this can create problem in our circuit. And to solve, we said the problem because of the discrepancy or multiple flip flops changing state. So gray coding is solution, and the ideal solution is to register the output in the next clock edge so that these glitches disappear, the valid ones come with a latency of 1 clock period. And we have seen that when we kind of do a little rework on that structure, you get a nice structure which can be the VHDL coding of that becomes very easy. Okay, so let us move forward to another issue, that is the selection of flip flops. Okay, now in all our discussion, to make things easy, we assume that we are going to use the D flip flops. All the time we said fine, I mean the assumption was that we use the D flip flops, but you could use let us come to this, you could use other flip flops like JK or toggle flip flops and so on. And let us take this transition, the present state to the next state. Okay, so like these are the possible transitions: 0 to 0, 0 to 1, 1 to 0 and 1 to 1. Okay, now in the state machine if you are using D flip flop, okay, the sequential circuit use D flip flop to implement the state machine, then we know that it's very easy. The input to the D should be same as next state, it's very easy, like we don't care what was the present state. If the next state is 0, the D has to be 0. next state is 1, D has to be 1, okay. But instead of D flip flop, if you are using a JK flip flop, okay, then that means like in the state machine, like what I am talking is that this particular flip flop, instead of D, if you use JK, then you have a J and K. Then you should know that for each, like earlier we had D1, say D2, D1, D0 coming out of the next state logic, but you have now so J2, K2, J1, K1, J0, K0. So in the next state logic we will add twice the output for the JK flip flop, okay. So if that happens, if we are using JK flip flop here, then the condition for that to decide when you work out the next state table, it will be like that. If the present state is 0, next state is 0, then we should disable the set, so J has to be 0 and K is don't care, it doesn't matter, okay. K can be 1, then it is reset, you know, the next state is reset, it doesn't matter. If 0 to 1, J has to be 1, it's a set operation kind of, J is 1 and K can be 0, I mean K can be don't care. If K is 0, it's a set operation, K is 1, then it's a toggle operation, it doesn't matter whether it is 0 to 1, can be a set or a toggle. Similarly 1 to 0, K has to be 1, it's a reset operation, and J is don't care. If J is 0, it is reset, J is 1, it's a toggle because 1 to 0 it toggles. 1 to 1, then that it should not be kind of reset, so K has to be 0, J is don't care. If it is 0 0, no setting, if it is J is 1, then it is a setting operation, doesn't matter. So that is what is the transition table for the JK, and if it is a toggle flip flop, then you know that 0 to 0 it should not toggle, so toggle is 0, 0 to 1 it has to toggle 1, 1 to 0 then toggle is 1, 1 to 1 it's 0. So toggle flip flop, by which I mean there is an input called toggle, and if it is 0 the output won't toggle, if it is 1 the output will toggle, that's the meaning of it. But looks like in the case of JK the next state logic will have to produce twice the output with respect to D flip flop. So you will find that internal to the next state logic there will be some logic for J2, some for K2, some for J1, some for K1 and things like that. And at least for a novice it might looks like the next state logic in the case of JK could be kind of little complex than the D or T, but mind you, you have don't cares in K and J in the case of JK, so that could kind of minimize the next state logic area. We are not able to say that. So though the JK case is different from D, you have the twice the number of output with respect to next state logic. Because of the don't care, the area of the next state logic can be less than in the case of D and T. Now that you should keep in mind, and when it comes to the FPGA normally you get D or T flip flops, okay. JK flip flops are not there. I am not very, I don't remember now, at least in CPLD you have an option of D and T, not because that in the state machine this is useful, but for counters you know that the counter has toggling action like at least the binary counter, you know that it counts very sequentially 0 0 0 0 1 0 0 1 0 1 1, then the next bit is toggle, you know. So the toggle flip flops owing to the counter kind of sequence, the binary sequence, this is useful in the counting application. So the CPLDs and FPGA has flip flop which can be used for the counting and wherever there is toggling application. So maybe we have less time left for the next kind of issue to be taken. So essentially we have looked at the 3 issues today. One was basically we have looked at the state diagram optimization, and wherein we said that basically the issue is to find identical state, and that is identical if both produces the same output for the same input condition and they transit to same next state for the identical condition. All the number of transition and number of next state should match, then they are identical. We have discussed how to kind of identify this from the next state table and output table, and somewhat formal steps we have stated, but it can be converted into a algorithm suitable for kind of software, can be implemented. Some tools implement that, you can check whether your tool implements it. And then we looked at the output racing, and we have said the gray coding is a solution, output registering is a solution. Then we have looked at the selection of flip flops, and you can use D flip flop, T flip flops or JK flip flops. In the case of JK flip flop, the next state logic has to produce twice the number of output, but then because of the down chaos the area can be less, but practically the FPGAs and CPLDs doesn't have JK flip flops, mostly it has D and T flip flops. Once again T flip flops are given for kind of binary counting, could be useful in the case of the state machine. Again there are ways the tools can choose the ideal type of flip flop, or you can kind of tell the tool to choose a particular flip flop if you are sure of the kind of some kind of advantage you get out of that. So maybe in the next lecture we will go look at the VHDL coding of the state machine. Since the state machine is an important part, we will look at it, not that we have learned all what is required, but formally putting it together, some kind of something specific to state machine coding can be discussed there. So please revise what we have looked at it, go through the timing, work out make some practical cases, think of when this is applied to the practical cases, what are the kind of side effects it produces, try to solve it. Or if you have done similar work, you think you connect with these lectures, those who are working in the industry, you can kind of relate to what you have experienced, what you have done in a project or in a work you are doing now. So please revise it, and I stop here. I wish you all the best and thank you.